In type 3 calculations, what will happen is you are going to be calculating the equilibrium constant, and you will be given initial concentrations and equilibrium concentrations of one of the items in the question. So let's go through an example to show how this type of equilibrium calculation works. So at a certain temperature, a mixture of H2 and I2 was prepared. So some sort of flask, they entered in some H2 and they added it to some I2. And what ended up happening was you produced over a period of time some HI. Now, again, we're at equilibrium here, so I should be using a double arrow. So there we go. What we want to do is we want to make sure that we have this as a balanced equilibrium equation. So I'm going to put a 2 in front. And I do want to make sure that each of these were gases. And we're just going to assume that because they haven't said otherwise. But I know they're gases. So what we want to do for these type of questions, it tells you that you initially placed some 0.2 moles of H2 and moles of I2 in a 2-liter flask. What we have to do is we have to convert those mole values into concentration. So we have to remember this relationship, that concentration equals moles over volume when volume is in liters. Now, notice that these are going to be initial values. So what that means is they're not going to be concentrations at equilibrium, but initially when they put them into a flask. So what we have to do is set up what's known as an ICE table. I stands for initial concentration. C stands for change in concentration. And E stands for equilibrium concentration. Okay. Now again, pause this video at any point. What we want to do now is we want to figure out what is the initial concentration of H2 and I2. So here we've got 0.2 moles in a 2-liter flask. So when I take that, I'm going to do 0.2 divided by 2, and that gives me 0.1. So the initial concentration of H2 is 0.1, and the same for I2. It's 0.1 moles per liter. Now, what is the initial concentration of my product? Well, initially at time 0, there is no product because these have to collide in order to start making some of this. So always, unless specified otherwise, your initial concentration of product is 0. The other piece of information that they give us in the question is at equilibrium, the I2 concentration has dropped to 0.02 moles per liter. So we don't have to convert that because that's already been given to us as a concentration. So they're telling us at equilibrium, the concentration has dropped to 0.02 moles per liter. So graphically, what is happening here? So let's just off to the side, just kind of construct a quick little concentration time graph. And let's just say that this is 0, this is 0.05 moles per liter, this is 0.1, this is 0.15, this is 0.2, okay? So what they're saying is initially, if I'm just gonna take a look at I2 right now, you have some at time 0, and what's happening is this is 0.05, then 0.05, 0.02 is maybe here. At equilibrium, that's when it starts to plateau, the concentration of I2 has dropped, okay? And we know at time 0, we have 0 HI, okay? So we wanna know how much of it do we have when it starts to plateau. What we do at this point in time, we have to take a look at how much did this concentration change by. So when it went from 0.1 to 0.02, what is that change? What we do is we subtract them. So we say, okay, if we went from 0.1 to 0.02, that is a change of 0.08 moles per liter. So what I do is I put that in my change column. Now, because that is a drop in concentration, I put a negative value. So we dropped by that much. Now, if you know how much one of the items changes by, you can figure out how much all of the other items in your equilibrium equation change by looking at your mole ratios, your coefficients. Because iodine and H2 are 1-to-1, what you want to do is you want to say, okay, well, this is going to change by the same amount. This is going to change by double that value, but instead the concentration is going to increase. So what I do is I do 2 times that value, and it's a positive change. And it's a positive change because concentration is increasing, not decreasing. So when you put in 0.08 times 2, you get 0.0 or 0.16 moles per liter. Now again, to figure out your equilibrium concentrations, what you want to do is just add your initial and your change column together. That's what it tells you to do here. And this concentration will be that. 0.16 plus 0 is 0.16. So what that's telling us is over time, if I was to track HI, 0.16 we'll say is about there. So its concentration will start to plateau around the 0.16 mark. So this is your HI. So its concentration is going up by double the amount, okay? Now, when you are writing a mass action expression, in order to calculate your equilibrium constant, you are only ever allowed to use equilibrium concentrations. Only equilibrium concentrations can factor in to your mass action expression. And remember that solids and liquids cannot. But as I mentioned earlier, we're going to assume that these are all gases. So when I write my KEQ mass action expression, it's always products over reactants. And you have to remember that not only did we have to apply this to in the change column, but it also has to be factored in when you're doing your exponents. Then I plug in H2 to the power of 1 multiplied by the other reactant to the power of 1. Okay, and I put in 0.16 squared. So I'm getting that right from my equilibrium values. And then you have 0.02 times 0.02. Okay, and when we plug this into our calculator, on the top, what we end up getting is 0.0, let me just double check that, 0.0256 on the top. And on the bottom, what we get is 0.0004. Okay, and you can probably do that all in one step, but when you divide those, you'll see that that gives you an answer of 64. And what does that tell you? Well, when you have a KEQ value that's a lot greater than 1, that means that it is product favored. So that means that there are more products at equilibrium compared to reactants, and graphically we can see that that's the case.